Hello everyone, welcome back to our Engineering Mechanics Dynamics class. This is our third lecture on chapter 14, Kinetics of Particle Work and Energy. Today we're going to just extend the principle of work and energy that we have learned in previous lecture. We're just going to extend that lecture for system of particles or for a rigid body other than just a mere particle. And also we're going to try to see how can we apply the principle of work and energy for friction caused by sliding. So in the picture you see ice skating, the boot. So the person is sliding on the ice, and how can we apply the principle of work and energy against friction that is formed due to sliding. So let's see. So the learning objective is extension of principle of work and energy. Example is that, like I said, for ice skating, the person is sliding on the ice and he's also working with the friction. So how can we extend the principle of work energy for application of this kind of friction scenario? And instead of thinking of a body as a particle, what if we take a rigid body, a big body which contains lots of particles in it, so like a system of particles. So how can we extend this principle of work and energy that we learn to these scenarios? So let's see. Extension of principle of work and energy. So let's assume a system of particles, a body, any body that has tons of particle inside. 1, 2, 3, 4, like lots of particles. So we're gonna take one particle here, and we'll assume that the particle is moving this path, along this path. There will be, so on that particle there will be force, external force acting, Fi. Let's call this particle as the ith particle. So 1, 2, 3, 4, 5, and it could be any variable. So ith particle, and then there is an internal force acting on that particle. We call it a small f, Fi. So this is this force acting on that particle. So there's two forces, external force and internal force. Internal force is due to the other particle exerting on that particle. So if there is a 10 particle inside that rigid system, so each particle is exerting force on each other. So that is the force we're talking about here, defined by small f on the I particle. So if this is the scenario, how we can apply this concept of principle of work and energy on this rigid body. So let me write, this is a rigid body. So we're gonna think that the particle is at inertial coordinate system. So let me write inertial coordinate system. So what it means by inertial coordinate system is that this is a reference frame of reference that assumes that a body has zero net force on it, and so there is no acceleration with respect to that frame. So the body is at rest or moving at a constant speed. So we're going to assume an inertial coordinate system, so that we can assume that the particle inside is not having any acceleration. So let's go back to our equation. Okay, before that, if we assume that the all the particles inside the body moves together when the body itself moves. So if this the entire body here, when it moves, the particles inside will go through the same displacement. So we can tell that the particle, the force each particle is exerting on each other will be cancelled out. So in this scenario, Fi will be 0. The summation of Fi, all the force acting on a particle, would be 0. So we can apply the principle of energy, work and energy on this condition. So we'll see. We'll start with our equation that we know. The initial kinetic energy is equals to the change of or applied work equals to the final kinetic energy. Since there's a lot of particles, we'll just do summation of those kinetic energy, and we can apply that for a system of particles. So this is simple. Well, if we assume that the body is translating, which in this case the internal forces will cancel out each other, and then we can apply. We can just sum all the kinetic energy of each particle together, sum of all the energy together, and sum of which will be equal to sum of all the final kinetic energy of the system. So this is how we apply the principle of work and energy on the system of particles. Now let's do our second extension on friction. So how can we extend the principle of work and energy for the case of work of friction? So how can we do that? So here we'll assume that there is a box, a force P is applied. Due to that force, a velocity V. Due to a fixed force, there is a velocity V of that box. So for friction, if we know that if the friction force, we can tell it as a coefficient of kinetic friction multiplied by the normal reaction n. So if we apply this to our principle of work and energy, we'll see the summation, the initial kinetic energy, work from position 1 to 2, and the final kinetic energy T2. So the first one, now since we're applying a force P, we're also assuming the force is applying P, which is just as equal to the friction which is against the movement. So we'll assume P is just balanced with the friction force. So the applied force is the same as equal to the friction force developed here. So there will be a fixed velocity v moving. So T1 will be half mv square, and T2 will be half mv square, since it's moving at a constant velocity and force is balanced. So P is equals to the friction force. So P and friction force F is same. So P equals to F. So there's no acceleration. So the final velocity and initial velocity is the same. So we'll have half mv squared on both sides. The energy we know is force multiplied by the distance. So if it's the force was P, applied force is traveled by a distance S, so PS. If P is in positive direction and friction is on negative direction, the friction would be coefficient of friction, kinetic friction, multiplied by the normal n, and the distance traveled by it is the S. So let's do correction here. We can just call the normal force as N only, then that way it will not conflict with this. So this is the work done, P force into distance S, and then the friction force multiplied by the S. So these equations to be valid, this one and this one cancel out, so we are left with P equals to N, which is the friction force, and that what we have assumed. So this is valid. We can apply this principle of work and energy for friction cases. One more thing, just for our understanding, that during friction, we know if there is a friction, if we rub something against each other, there is a heat generation. So how do we consider for that heat generation? So in this concept, we have to assume that the body itself is deformable, and let's see a scenario of so the box is moving and it has a surface micro. If we see it in a micro level, so this contact surface here, we can draw it as a like so. So the surface of the box, lower surface of the box, and then the contact surface of the sliding path is kind of rough. So this is the contact surface, and they're gonna be heat generation. Now if we assume this material, the block is deformable, then what will happen? Either the small tiny teeth will break, which in case sometimes we see if we rub something against a hard thing, for example a wax on table, so you'll see the wax is on the table, so the wax is being deformed or breaking off from the and getting onto the sliding surface. So if we assume that, then that there will be some localized deformation, all those contact surfaces, and that will change the displacement. So we assumed the displacement as S here. So that will change the displacement due to localized deformation. Let's assume that is a S prime. So S prime will be always less than the S, and so the friction will be changed. So we will have the frictional energy, kinetic coefficient of friction, normal force, which is normal from the reaction of the weight of the box, right? And due to localized deformation, we will have actual energy of friction is this, and this change this change will be the internal energy, which causes the heat rise. So we're gonna kind of neglect that. So just to summarize, we will have the resultant friction that we're gonna use as we're gonna assume that this represents the frictional force itself, the actual frictional force itself, plus the and then the internal work, which is N S minus S prime. So it's just for our understanding is that we will consider the heat rise in this form, and we're just going to use this equation mu k n multiplied by the distance, and we assume that this includes the actual friction force and the heat rise. So this is how we're going to apply the work of friction on principle of work and energy. So that's it for today. Thank you. See you in next lecture.